Oh, good evening, ladies and gentlemen. This is your usual brother, Engineer Michael Chola. Today, I'm just continuing with the Balanced Cantilever Bridge talk. I think sometime back I hinted and I posted, I think, at the respan Balanced Cantilever, but then also said after some time I would come back and we share more knowledge. So basically, that is something that I decided to just share with you. This is a balanced cantilever of about 1, 2, 3, 4, 5 span with twin columns, pier columns, and there's a tapering deck, which deck is a single span, not single cell. Box girder. This is the shape, and it's actually across River Nile. It's a bridge under design, but this was an independent design check. That's also a learning session. You know, we have to also learn. So we have a consultant doing a design. They're using CSI bridge. At least for me, I said let me also use Midas and see how best we can generate. So I did that, and so it's now we are busy reviewing. You compare, we normally compare the made presentation. We also do and look at it, but definitely these are very senior consultant in Africa here, maybe also across. The consultant is called Da. This bridge, I think, is crossing at Masindi port. It was designed by 2013. It was in total it's 514 meters. It has a center arch piece. I would have shown you here, but there's no need. We'll get maybe one day. So it is full. It's a twin steel box girder, composite box girder, and the arch also is full of steel box. And then we try to look at issues to do with cost. I think the cost of steel post-COVID was really skyrocketed. And so when we asked the consultant to do a value engineering, putting into consideration the policy that government of Uganda has to buy Uganda product and build using Uganda product, we discovered that for structural steel, almost 70% of material would be imported, and therefore with this local content policy we wouldn't get anything. So we decided, okay, let's have maybe concrete, because with concrete that means we are left with importing only some few technology and material like strand for post tensioning, but materials of basically construction material, the imported approach roads, the box girder, concrete, aggregate, sand, cement, all produced in Uganda. In that way, I think because of availability of material, it would be fairly okay. So I think based on that, they did a review, and they are going to adopt that. I will show you briefly a small elevated AutoCAD drawing. Okay, that is briefly about that. So this one now is 550 meters, the outer span, 52 meters, and interior span, basically 90 meters. So this is integral, pier integral, though outer span has a continuous, simply supported to allow movement. But this one, I think, for me, with my independent check, I move in with this all cast all together, integral in functionality. So basically, that is briefly about that. Let me now go and we proceed slightly. Okay, so this is the view of the balanced cantilever. Of course, in reality, from the drawing, it is doming, because it is here would be like 0 towards the middle, almost like maybe a meter or 2. and the central span is done to take care of navigation. I think Masindi port in the 70s and 60s was known for what? Was known for navigation, and therefore we have to observe the issue of navigation. And also most of our bridges now crossing the major rivers like River Nile, Lake Victoria here, then Lake Albert, Lake Kyoga, it has to take care of navigation. So we are very keen on that, because we also have some knowledge on long span design and construction, and so that we have to take care of. So this is the bridge. That is the typical pier is about 7 meters. This is about 13.6 meters. It's so when you look at it, it has a tapering. It has tapering at tapers here, and then not thicker, deeper over pier support, but and then narrows to the closing point. This is the close around here. With a span of 90, that means this is about 45 from the center. Okay, fine. That is briefly about that. But so before I go into the details of just briefly about what modeling is all about, I also needed to just quickly take you to just feel, you know, when you are reading, sometimes you also have to do some hand calculation. We don't need to depend on handwriting. We don't need to depend 100% on typing and copying from what. So Balanced Cantilever, I think there's some book which I read, and I got some notes. I think we shall get reference down. So when you talk about Balanced Cantilever, so it's actually here is the application. So the structures, this Balanced Cantilever, these are bridges which involve high pier support, and with the span wide, which span wider gap and deep valleys. So areas that propping use of scaffold is a bit difficult. The preference bridge normally takes the shape of Balanced Cantilever or a Balanced Cantilever. So you can see which is centering is also actual application of scaffolding. So very costly. So to avoid that, you do Balanced Cantilever. We shall see what it is. It also crosses rivers with wild and sudden floods, dangerous to center or to centering. Centering is another word of scaffolding, application of propping system or false work. So rivers which have dangerous floods at time of rain, and also very deep with sudden flood, normally application requirement is for bridge engineers. They always go for Balanced Cantilever. And so if you need to allow the flow of certain volume of traffic, or to permit navigation while construction is in progress, you always also apply that. So it doesn't allow centering, or doesn't allow scaffolding that blocks the obstruct traffic, which can create safety issues. This Balanced Cantilever normally span between 50 to 150. But as you will see down there, I think we have bridges that have gone past 150 meters. The center span, they are 200, 230, 200. I think with maximum, I think now is the championing bridge now is in Japan. So we shall look at it. So that is what we will look at. It is the most frequent span is actually 50 to 90. Because constructability, normally if the span goes towards 150, then as you build the bridge deck, where you start with the support system, then you can symmetrically cantilevering, moving outward from the pier support. It has to be balanced. So if you have an error in the length Or you can, if you're doing segmental and you place one segment and the other one is not, then you create imbalance. That will become an eccentric loading with also construction load and equipment on top. Then that becomes a problem. So with long span, normally by the time the closures are meeting, definitely you can get problem with the high stress area like the pier support system, foundation pier, because with pile system you will be having push-pull effect, and so all that need to be taken care of. So the most span, I think, on 50 to 100 or 100 Mark 20, that is they say that is fine. So the maximum span now for center bay across Rhine is 208, while world record is 240 span. So you have a 240 meters middle span. You saw it from here. The middle span here, it is actually the one over Rhine is 208, but the world record is having 240 at this point. So basically that is what they're saying here. And it is called Amana Bridge in Japan. It was completed in 1976. You can imagine, complete in 1976, and if you look today, is basically close to 49 years now. And then this is the Benford Bridge. You see the center. You see the center here. This is actually the one. This could be the one with this center bay having 208 and even 208 here. Then you have also Ikoshima in Japan is 236, and then you have Benford 208, Orato in Japan. So I think Japan has more longer span than 150. Than any other country in the world. Philippines 240, also I can see record sharing. Orato Bridge 230 in Japan. So some of these sketches. So in France you have 2 number bridges with span exceeding 150. So I think now this is an option of a bridge that can actually dominate, especially for us in Africa where we have river bridges, but the rivers are not very much wide. So could actually do that. So now you can see the different spans, and so then in France you have that Geneville's Bridge 172 meter. It was segmentally constructed, and then you have Calix Viaduct in Caen 156 prefabricated center segment. Now, being concrete, you know, concrete is very heavy. And so some of these bridges now you can see here that this is 150, 171. They are using what they call lightweight concrete to reduce the weight. Though lightweight concrete has its own functionality, resistant challenges, but they try to reduce because the cantilever, because if you're constructing, the cantilever effect is too much on this pier support. And you see it is actually simply supported. So definitely you have to do a bit of supporting it at the pier support here. You support it all the way in a way that around the pier table. Then you carefully place your overhead gantries. If it is cast in situ, then you use foam box traveler. But if it is sometimes they use overhead gantries if it is precast segmental, and then you do it. But this is now the introduction of if the span I think exceed 150 and above, it's important to reduce the weight of the then the deck design. You can see here they are saying this bridge is built symmetrically outwards for piers to avoid high asymmetric cover turning moments in the piers. I've told you that it has to move uniformly with no difference in the loading as you go outward. As you go outward, this is your pier, and then you are moving. Every time you put a cast, you move. You keep extending your foam traveler until you reach what they call the closure point, and then you tie. When you tie, then now that's when continuity comes. So the cantilever effect is reduced, it becomes continuous once you do the closing. So this is balanced cantilever is actually coming out from the balance construction process outward from the pier support until you close. So build symmetrically outwards for piers to avoid high asymmetric overturning moments in piers. not possible in practice. So the piers sustain some stresses and bending. And so that is why when you look at, when you put the foundation pier pile cap, then you build the pier system up. Before you start moving out, the construction of the pier table has some propping system, and as you are getting outwards, so normally they also tend to prop so that you try to limit that the high stresses around the pier support, because it is not possible. Because as you place those construction loading and equipment, there are always some people will move the other side, so the live load from the human being and other thing can be more the one side, the other side. So in a way, you have to try to stabilize, because stability is very important. If you're subjected to wind, as the arm get longer, it becomes unstable because of wind swaying in the y direction. Not okay. Assuming that wind is perpendicular, y is perpendicular to x is the length, is the direction of the bridge. So that the wind will definitely affect that. There is need to provide temporary fixes between deck and pier support during construction, wedge and stress tendons, or provide temporary support to during the construction. This is if it is simply supported, but if it is cast in situ, where it is this side here locked in deck pier, these accommodate asymmetric moments during construction more easily. So there's some problem here why you have to prop it if it is simply supported. But if it is monolithical, the deck system is monolithical with the pier support system, then it takes care of eccentric, but still you need to calculate and also carefully monitor and do your quality checks during construction. That's why during construction the contractor also is required to provide simulation designs based on the available material, equipment, their sequencing of construction. So that is very important. This small page here is actually the whole thing. Balanced cantilever. You have segmental construction, and also you have cast in situ, whereby everything you do conform traveler and move, while segmental they do overhead country, because now you have a prefabrication yard. You fabricate these the segments. We shall see, I think, the sizes, the dominant sizes in the industry. Okay, so that is that. Use of temporary support needed for asymmetric construction. Definitely, I was trying to look at that bridge I was talking about, which is across the River Nile at Masindi port. They have 52 here, 88 and 90, and also a bearing here. Definitely here you have a continuity, but before you reach here and here, there's an imbalance here and instability here. So that means you need to have a better, once you are done with pile cap, then you build this one, you have to, and when you start the construction of the pier table, you need to prop this system in a way to cause to do a bit of balance, because 88, and if I'm to balance, it will be, that is a half of this is if this is 45, this now remains 45, from that remain 43, and then 43 here, and that means now I need to make sure you under. So this balance is done under false work. But towards the abutment. So but the next pier 2 onwards, they are monolithically cast, locked in. So that is how you look at. So overturning implication is here. So this has to be taken care of, properly simulated by the contractor, cross-checked by the engineer and the design also, and then carefully observing creep and shrinkage issues and temperature issues, eccentric loading in terms of the live loads and the rest of it. So I also looked at some literature, and I found that actually all French balanced cantilever bridges construction, the construction since 1961. It's good. That's how they did, and better inch construction. So, and that is that. So vertical deflection or ask. So this is now at a closure. So they are actually trying to say, once you build your bridge now towards the center now, because there's imbalance, for you to have that alignment, proper vertical alignment and horizontal alignment. You have to control every stage, considering shrinkage effect and creep effect, the wind issues, and many things. So you keep checking. Accuracy is very important. The survey, they have to be done well, and then you are construction monitoring and observing the difference in temperature. So the vertical deflection control, and then you have to look at. So this is how they do that. Keying, this one sometimes it is closure or keying segment. It provides continuity. Once it is closed, it provides continuity of deck to ensure ensuring by integration cables tension after hardening of concrete. So you have to tension that section after hardening. So that is that. It is located in the lower. So the cables are located in the lower flange. So now once it closes, it becomes statically indeterminate reaction, which must be considered in your design of the deck. When the thing locks in the closure, then the structure becomes indeterminate. That is something that I picked, which you can also look at and read more. Bending moments due to linear phenomena, variations of temperature, moisture, shrinkage effect, all that need to be considered, may be increased if construction takes place with large difference in temperature occurring between the upper and the lower flanges of the cantilever. So at this point, because of these varying loads, moisture, temperature, shrinkage effect, wind, and the rest, you have to have a temporary tensioning here to keep. Once the two arms are now meeting, because it will keep moving, it's also moving, can move like that. So there is a vibration. Aerodynamic effects come in. I have not done that, but at least borrowing from the Nile Bridge and also reading about aerodynamics, definitely something will happen. So the temperature, instead of if it is hot, the bridge tends to breathe in, so it goes bigger. It tends to move. Then it also breathes. So it contracts when the temperature is low and expand when the temperature is high. So with that, wind also is happening. Upward wind, sideways wind. You know, wind can have an angle of attack. From zero, moving down, moving up. You have seen that curve. So definitely here you have to be careful. So there is temporary variation can cause deformation, and therefore fixing top of the cantilever ends to avoid deformation affecting closure. Temperature variation affect the control. So it is very, very important that at the closure, please, you have to. And that's why sometimes supervisors emphasize some quality checks, and they also emphasize you don't just need to rely on the engineer's design, because bridges are site specific. So when you are constructing now, like if you are in the center of Uganda here, central Uganda, the temperature could vary maybe between 17 to maybe 27. As you move towards northern Uganda, it's jumping from 21 to 35. So you can see it. And then variation from morning, midday, afternoon, and evening, and night. So you need to be very, very mindful of that. And then that's why the contractor needs to have some design engineers also to help make sure that they also carry their parallel design. I like the approach of Japanese, where the consultant normally do preliminary, but most designs are completed and handled by contractors. I think even Egypt, I think they have that. They do the design, but the contractor is given the responsibility to take over that bridge and the design and make it constructible, buildable, while observing design functionality and then other things that require the bridge to work. So continuous systems are ultimately statically indeterminate and a self-weight and pre-stress, and their degree of indeterminacy is higher than that of hinge system. So once, okay, you also know that in most countries before experiencing challenges arising from use of hinges or hinge support, where these cantilevers will come at this point, you don't join it. You have a hinge support here with some bearings. So you find leakage, and then failure happens here, shrinkage problem, creep issues, deformation, and many things with time, and due to cyclic load and temperature and the rest of it. So all that always cause a bit of challenge and so you find that the continuity, in a way, try to erase that problem. So that's what they were saying, that continuous systems are ultimately statically indeterminate and a self-weight and pre-stress, and their degree of indeterminacy is higher than that of Anced system. So long span continuous balance could require expansion joints between 300 and 600 apart. So if the spans are not all that between 300 and 600, then you don't need to have expansion joint. Now you can see the use of expansion joint midway. This one has implication with time due to creep, deformation due to creep and shrinkage and the rest of it. So it can also, if expansion joint is not done very well, leakage start from here, and this being highly tension, definitely you can get a lot of problem. So this construction more or less is being discouraged in a way. It will actually move towards the support if you want, and they are telling you these are the requirements where to place some of these inches, so you can have a look at. Then down here, this is also the closure or keying segment. So they are telling you how to detail. How do you detail here? Please, engineers do design, contractors do construction, but you must have a good detailer to understand, and then the supervisor must be, because here they're telling you there are integration cables, then you have cantilever beams, then the rates are cantilever beams coming from here, then the closure, because the bending is now downward, this part become tension, here become compression in a way, and when it closes, if not, up would be tension, down would be compression. But now once it closes, it becomes continuity, and this is what would happen. And if I can quickly take you back here, and oh, this is, I did not run this one, sorry, I would have actually given you the moment, but what could I could actually check something quickly for you here, and then try and see what so Masindi port combine. So for that combine, I can look at the bending moment quickly. Now that we are, I want to show you some bending moment. Okay, where is the completed bending moment? Here, to demonstrate that this thing become continuous once you close it. There we are. So where can I increase this? So you see the closure I was showing you, this one here. So you have a closure here become moment, but as you come near here become, so I think I should be having it that side. So here now, so now this blue become continuous after you have closed the closure, the keying segment. But without that, I can also show you somewhere. If you have not closed it during construction, this is what happened. You see here. So now you are moving. When you start it here, now this is yet near the support system, peer support. Now you are moving outwards. You are moving outwards. You are moving. It's about to close. As soon as it closes, it changes, and then in service. Now that is for the deformation. This is at what you call construction staging, but with time, when post-construction stuff, then you are going to have it here. When everything has closed, then this is what happened. So that is how then you have to be mindful here that this here. So you have to be mindful at this point here is what it is here. So the key requirements are design and construction stage. You have to be mindful. Detailing, how to detail this, how do you make sure this point has not disfigured. It allows that meat, symmetrical meat, aligned properly. Not here you're pulling it here, pulling here to come. But definitely now with the top stressing bars, post-tension bars, you keep it and then you close it properly and allow it to set, and then after some time I think you should be able to remove. So long span, it permits expansion joints. Problem can be solved by the flexibility of, now this is when you have this monolithic connection to that. So peer pier themselves or using elastomeric bearing or sliding support. That is what they're trying here. Quickly, they're telling you that if the main span is L, the outer span is about 0.65 to 0.7. Many countries have different formula for this, but definitely I've just discovered, okay, fine. Others do 0.5, others 0.6, others 0.65 to 0.7. Oh, so that is what normally I've seen, and we are going to see some tabulation down there how the different countries do that. So consider vertical deformation, angular checks, and the rest of it. This is now trying just to play around with how do you make sure half. That's where you have to have your. Then what remains is what goes on top. Sometimes you can allow this to be exactly on the abutment or then midway here. Now, so the reference here for this note is actually the cantilever construction of pre-stressed concrete bridges by Jacques Mathivet, translated by Mrs. C.J. Emberson. So this is the, if you get this narrative, you get that story above. So it's not my knowledge, but I just read it. So this is another cantilever. Can care to be taken to avoid lifting at the abutment point or hogging effect for cantilever, for confidence. So here you have to be careful. It should not lift. That is why sometimes it's slightly longer to allow it to rest, and you have a behavior of this nature. You have a behavior here, so you can actually see. So you can actually see that you have this is now the one. If you leave it to cantilever, it's not good. So allow it to bear, and you have a bending here, and then the whole thing works, flowing very well. Okay. In practice, provide end span with always positive reactions on the abutment. Good practice to avoid use of a device to control uplift. Very well. You see now this one? So this one is not bad. This one, I guess it works well. So this is implementable. But with review, definitely you have to do review. So that's what it is here. And then centered by adding, catered by adding 1 or 2 segments. So if it was 45-45, the balance, I told you it was 43-43. Now you need to add 2 or 3 more so that it pulls it down and create a bending and reaction kind of. So the other, because the other cantilever is going to marry with the closure between the two, the main center span of 90-90. So it is very important that, but if there's also eccentric behavior, there's also what they call use of, there's that concrete you add inside to balance. Balancing concrete, you need to have, if it is not balanced well, like the 45-45 for 90-90, then the 88 becomes 44. So 44, a difference of 1 meter. Still, there's going to be some weight balance that need to be done. Okay, so catered by adding, and so no need for false work as use of counterweight. Counterweight can handle. Counterweight is what you can do, put inside the box. So web spacing is limited by transverse bending. Okay, now this when you are sizing what? When you are sizing these members, and you can see this is double cell, this is one cell. They are telling you that you can save 8% of section, 3% total in total if you remove this and allow that one. These are the savings you make. So normally you have to be careful introducing the middle web. It has implication in terms of additional concrete, reinforcement, and formwork, and complexity in constructability. So of course here they tell it has high local bending moment to webs, modest span to avoid transmitting. So here, to avoid the transmission of moment onto this web, you make sure between 5 to 7. Sometimes if it is too much, you do cross beams, and then also you do the what they call transverse post tensioning. Deck width greater than 13 meters, use 2 webs. Now these are some countries. If you go to other countries, it is up to 15, others even up to 18. So it is very interesting. If you're in France, they have their own ways. If you are in Norway, they have their own. If you're in Japan, they have, but very interesting. But of course, as an engineer, you run also your own design to check. So that is what we have. Now this is another reference. Concrete box bridges by Joe Silaik Hartmut Chef. This is the name is very complicated. Look like Russian, well, German, and I don't know which one or which one. So basically, that is what you have, and then here they're indicating that the orange thickening of the bottom flange over pier support should be about 1/10 of the span thickening here. So these are guides that you need to follow, and these are also some of the incline web, vertical web. They have their benefit and risks, construction challenges, design challenges, functional challenges. So these are things you need to look at. To simplify formwork, vertical webs are therefore selected. Simplify formwork. But when I think when we're dealing with LAROP, we check the difference. Of course, not too much. It's not too much, but there's a bit of stability in one over the other. So the orange here is given how to get the orange distance, and then because of formwork, they're telling you if it is 0.2, it become problem with fixing formwork. So 0.5 normally works. So these are different thicknesses they give. I think this was something. So here is another book, Bridge Engineering Handbook, edited by Wai Fa Chen, Lian Duan, look to be Chinese. And so with the balanced cantilever, they have span arrangement, constant depth. If you have span within 50 meters, you can do balanced cantilever but with constant. And if the depth exceeds 50, then they start using varying what? This one here. This is varying depth. Here is 3 meters, here is about 5 meters. Okay, fine. So that's what it's trying to say. Over pier support, we are using L/18 and mid span L/30. So if your span was 90, divide 90 over 18, you get the depth over pier support, and then L/30 you get. So if I can show you this one, not this one, that one. Here is L/18 to get that depth, and here L/30. But normally it is 30 to 35. This one also, some even others have L/15, L/20, L/25. We shall see something there, and it's very interesting. Okay, so then the orange length is about 20 to 25% of L. Now you see this is now Wi-Fi, but the other guy there, that gentleman whose name was very complicated, is L/10. So his orange seems to be shorter than this one. Single cell box, okay, economical. Double cell, more formwork area. So now you have to be careful with that. Incline web versus vertical web. Now here, aesthetic, okay, but difficult in formwork when used in combination with varying depth. Incline has a problem, yeah. Construction, you are moving, curving, and also the slope is there. So you can easily get it wrong. The area of the bottom slab over pier support is determined by the modulus required to keep bottom fiber compression below the allowable maximum at this point. So these are some guidance that we need to follow. Web thickness depends by shear consideration with minimum of 250, no internal tendon, and 300 when you have internal, because tendons have sizes 50, 60, 80, depending on the span and how much the stress it is. So this is basically, okay, this is a typical one which I was trying to work on. So trying to check, this is how the details was. Of course, you have to check geometry, structure, safety, geotechnical. So these are some of the parameters we always need. So some literature here was given somewhere, they talk of formwork traveler about 400 to 1,200, and that's about 40 to 120 ton. Normally for mine, I see that you can actually change it. They normally have default, I think 70 or 80 ton. Construction equipment tip. At the tip of the cantilever, you also need to allow 1 to 2 tons. That's why sometimes if they are not correct, then you have the imbalance, and then you have eccentric behavior, overstressing some of the sections of the pier support. So you have to prop it in a way. Construction live load is about 0.5 kilograms per square meter applied on the deck. So these are some of the rule of thumb, but it's good to cross-check, get some literature and check all the wind loading on the deck, including upward wind under the of the cantilever, underside of the cantilever. You do sideways, and also you have to consider when it is going up. So very, 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 very important. Also use 2.5% of heavy concrete on one side of the balance clearly to create that imbalance, to make sure you creating a system that will not have problem during construction. Then the issue of cell weight is always taken care of by the software. This is superimposed dead load, wearing costs. Then there is a crash barrier. You have raised walkways. You have quite a number. Wind is here. So these are some of the things you do for your work. Now, when you are modeling, some of these sketches help you a lot. I always tell people that you must have some sketches to help you. Traffic, this was SV196 being used. Stability, you can see here 1010. You have some loading, you don't have the run. All that has to be taken care of. Twin leaf deck built integral with piers limit the out of balance moment from the construction without need for any temporary use of temporary works. Twin leaf arrangement provides the necessary moment restraint during construction without being too stiff along the deck. So the cantilever segment they have given us here, I told you it varies between 3 to 5 meters. Section cast of that. Cycle for each segment is about 7 to 8 days. Others have even to 12. So different authors and different exposure of that. Early high strength concrete is required because you need to start moving, loading early. Economic to span less than 100. So that is basically what I think we have. So that is we need to know about that. This is another literature, I think, pre-stressed concrete design and construction by Nigel K. Hossein, construction by Balanced Cantilever. Short span deck within formwork traveler length, form of casts suited for long span bridges where access to beneath is difficult. Fast flowing water, we already talked about it. Deck is built from pier support system outward of each side of the pier, at a balance sequence to minimize the out of plan forces on the pier. And then when building cantilevers have been completed, the keying segment or closer is constructed to allow for continuity. I told you, and you have seen that. End span usually 60 to 65, and you see this is now also from UK. It's 60 to 65. The other one was 65 to 70. So very, very important. That's different literature guys have their different stuff. Okay, fine. This is very important. So this is what normally guides some literature that you need to look as your model. So now when you come in here, so these were the modeling that which we did. I can take you back here quickly. So from here, these are the modeling that I always talk about. You start with the materials. Once you do materials, you come to, this is materials. You have to specify your materials. And then you come down to tendon material. You come to shrinkage, defining creep and shrinkage. You have to do that. Time-dependent material function, compressive strength of concrete, time-dependent compressive strength. Then here you have the tendon requirement, internal, there's also external. Then this is the total area of the tendon. There you have a duct area. Then you have ultimate tensile strength, the yield, then coming down. So, and then you must also be aware of the slippage at the anchorage slippage. That is very important to look at that. So this is now the model. But when you open the wizard, this is the wizard. When you open it, you find these wizard requirements, but you need to also know the component. I think what I needed to show you, anyway, I cannot get that quickly. So this is that is the wizard you have here, and then all the requirement, material gather, material for peer, number of peer support system. You have all these details that you need to put in place. The peer table placement, member age, the zoning are all given here. So it's actually user friendly. I've raised an issue whereby this need to be also doming. They need to have Moida's cut. The attention need to work on this, that we are able to adjust the length for the individual one, so that become better. Okay, so modeling using that. So this is for typical section. You can see a section here. These are the requirements. You need to have your section. If it is double, this is for type 2. You can put in that sloping issues. So you have a model section and then the tendons. So once you press all that one, you should be able to run in your model. So this is now where you put in your concrete load. Then you have what they call the traveler form. Okay, fine. So we come down. This is now when you're pressing tendon requirements. They're all here. This is now when you are done with all, then this is what comes out. Then from there, there are other things you have to these are typical section. Now these are the sections that appear with all other requirements, so you have to have that. These are different sections that are come. So all those segments, all they all can appear. So but this one, the problem was giving the I and J. All those sections have I and J section, then beginning and the end. So that's why it's appearing 2, 2, 2. But otherwise I would specify only I or J. So you have all these sections that you can look at, but you will have provided it in the model. And then always important, you first draw a sketch of the AutoCAD, understand the segment, draw it, understand them, then you start. So this is the output. These are reactions that you can look at, the typical reactions. But you can pick this reaction and design the peer support. No, pile caps. Then this is now when the whole moment is in place. I think service. This is the shear forces, very high value. This is now tension. You know, when you're pulling, using those blisters, anchored block areas, you have axial forces moving in line with the bridge, high at the support system. So it means your section also should be able to resist compressive. It allows that compression. Then you also have deformation creating tension and also hogging. So you have tension, but normally this category of post tension, sometimes you don't need tension, you don't need crack, or if the crack is there, should be minimum that is manageable, because for post-tensioning bridges, if subject it to allow crack, then you have contaminant ingress into the ducts, and corrosion can happen, and everything can get loose, and bridge can fail. These are construction staging. This is over the pier support. As you start moving out, you can see changes in the moment start moving, and then as you get farther away towards the mid-span, you see the moment development. During construction staging, construction loading, self-weight, equipment, traveler, you see even how the support system are also experiencing increase in the moment. So that is normally what you experience until the thing meets, and then actually you're supposed to have. Now after it has closed, you can also check the stresses. Which stresses I think should be somewhere down here. Okay, these are this is now how the whole thing is moving, and then you are able to look at it. This is the stresses that you have to check. Once the thing, this is at the end of construction, you can check. This is the limit. You look at both what they call tension and compressive forces and stresses. That should be within limit. So once it's there, then you can put. This is now the camber controls. So camber controls are all here. You need to be mindful. 1, 2, 3, 4, 5, 6. So you can look at this camber, and this is what you need to do and check. So camber control also is there. Then I think after that, now you can do what they call, after you have done all the rest you put in, then you can do a design. Over abutment, this is how the design is handled now. So now you can see, you know this design section information. You have concrete materials, reinforcement material, tendon profile, then ultimate moments, resistance, all start coming in here. Now that's where you now open your real reference text and manual to know whether the design is okay or not. You come down here, So it will have all these checks. You can see after checking moment resistance, it's saying it's okay. That means reinforcement. You put the negative moment also is being checked. It will give you either it is passing or not passing. It's also saying okay, but summary it fails. Yeah, so depending on reinforcement you have specified and the post tensioning system and the section you have specified for concrete, you should be doing. So this is now testing P segment over peer support. You have to also check. So when you check all this, you find some are passing, even this is passing. Okay, and so you have to so see, you're also failing. So this failure, you have to cross check your sections and then make sure you checked everything. So this is for peer support. Then I think after that another check was somewhere. They're basically similar, so that's why I'm just scrolling. If I get somewhere where we can save this, we could save it as narrative for you to check. I will check if there's anywhere I can post this as an article. I will save it and share with you guys. So these are some of the checks. So also here for the peer support system, you can model this abutment. You model it properly. The good thing here, we are using Midas for everything. You model your abutment support, put in the spring constant, everything generated, have those geotechnical information, model it. You can see how it behave. Then now you see this, you calculate all that. Even these are the different forces on the piling. Then also you can get that. Then also these are different forces, stresses in the plate of the abutment, and then it has a part of this is buried. It has a column going down and then piling some. So that's the thing. And then also try to look at these are just trying to go further like an artist to see how the contours behave on the abutment and the pile cap. So now after that you design it. So now here also using solid, you want to see what is the implication of bearings on there. You can see the bearing. That's why there's a lot of, you have to double layers of reinforcement, because there's high concentration of stresses below or beneath the pier support, the abutment. You see here, this is the location where you have a, so you have to be mindful of how it is. These are two bearing locations. So putting it, so that's why the distance between the bearing and the edge of the wall is very important. High stresses can cause spalling, so you have to be mindful. These are now the design. So this is just a normal design that you know it is okay. So this is for the column. This is for the column, and this is check. You can see most of the things are passing, the different column sizes. It's very interesting. Okay, it's steppering, but I use because Midas cannot design steppering, so you just convert into rectangular stuff or square. So this is the abutment. So abutment also has something here, the normal design. So this is the piles for pile cap. Pile cap, I told you can actually do. So this pile you model to take care of the water. You have a water here. This is the river bed area. This is now where it is anchored here. So it's subject also to lateral loads. So that is the pile. These are the pile forces. Then from there you get into the design, pile caps. So all this you check against what the consultant has done. Then if it is not working, then you share with the consultant. Then they see what they can do independent. So this is that is it's about 1.5, about that. So these are the different piles. Okay, fine. So repeat it. So there's no need to waste time here. And then this is the outer pier. I told you the outer pier is this one. This is the outer pier, 3 meters by 7, and it passed very well. And when you find it agreeing with what the senior consultant has done, you smile because you are new in the whole thing. So this is the transverse effect. You can do as linear meter and check. Sometimes this also helps you to size the section, and then yeah, you can do that. So I found that actually it needed more reinforcement, or it also needed maybe to be reinforced with post tension transfer, but the consultant has done their detailed design, so I let them handle that. Okay, so So that is, these are design output of this. Okay, I think then this is this is okay. I think it's repeated. This is peer. It's repeated, so it is peer and also that transverse deck. Okay, fine. Okay. So this is something to do with stability and balance construction. I just hinted a bit to be observed. Water level, this is now water, this is river bed, so definitely you're going to have a bit of challenges. So when you're constructing coming, all this has to be, but if not, then you have to make sure you prop this is how to construct pile cap and up. But some recommend just to make here, which is not a problem. So need for propping system, this is how the whole thing looks, and there we go. Thank you. But now I have something I need to share. This is comparison table. This one, this is, if you look at two, this is a balanced cantilever balance. This was Karuma in 2022. We're also doing design, but it has moved to extra dose. But I wanted to show you that even here in Uganda, I think we are moving towards very interesting bridges very soon. This is Maxon Falls along our river Nile of Karuma, so you're going to have a good one. The design is there going on, but this was the earlier one. But for me, I can model. I do this to practice another thing. But it was because it was heavy, so they had to modify, get something which is cost effective and lighter. Cation piles or foundation was being proposed now. It is because it's rock, they are going to use spread footing. Then down here, this is now the one we have been looking, the one I checked. You see it is curved, but my check is not so curved. So this mine does need to be flexible. If the wizard should be flexible to adjust the vertical grade, then that is done. Then we have a Laropi Bridge, also downstream to connecting to Moyo from Gulu. You have it's a 1.5 kilometer. We had done a balanced cantilever up to 150, but I think Arup consultant reviewed and they advised that we can reduce to about 120 constant and then 8 a year. Now this 8 now is it 0.7 or 0.65? You can check. It is 0.67 actually of that. Then the LL. So now these are some of the common bridges we do. So that means when we are talking to young engineers, we have live example home here to talk to them. But basically, these are some of the bridges that we have. Now, I tried to look at the different bridges, comparison of balance cantilever span to depth ratio. Japan, Kiso Bridge, span to depth ratio at PI is 8 to 12. Span depth ratio is 15 to, that's mid span, you can imagine. And yet in the modern construct, we have 30 to 35. I think they have done research and they're doing economy and other thing. So when you look at this mid span, they are within 15 to 23, while at peer support is between 8 to 14. And yet now we are in 18. You saw one bridge was 18. So these are the center span. These were earlier construction, but now with development, it has now moved. But what are the observations for this kind of choice? Peer support ratios are generally lower due to high load concentration and structural reinforcement. It has to be deeper and it's cantilevering longer, so high concentration load. Mid-span ratios are higher to optimize material efficiency and load distribution. You don't need to take the entire depth all the way to the center, become too heavy. Then Japan, Korea prioritize the seismic resilience, leading to lower ratios at both peer and mid-span. Now you see the preference. That's why different countries are different ones because of their preference of choices for load response. France and China emphasize the aesthetic integration and large-scale infrastructure, allowing higher ratios. Britain and USA follow conservative engineering principles, ensuring long-term durability. And then Germany focuses on precision engineering, balancing material efficiency and structural stability. I like German here. Precision engineering. This is interesting. Very good. Very, very good. I think they have very sophisticated technology. Wind, you have to reduce wind, maintain wind and temperature, everything. India and Egypt adapt designs for monsoon resilience and desert climate, ensuring high load capacity. These are some of the things, site-specific, country-specific. This is interesting. Then Norway optimizes for harsh weather conditions and ford crossing requiring advanced material. Very good. Then down, I did something quickly using AI just to guide. I know it's not too much, but I'm trying to look at how do we generate national annex. So I said, okay, fine. We have districts in Uganda, so many, about over something. And I said, give me average winds. Let's also look at the minimum and the maximum temperature, and also peak ground acceleration. Try to look at it, and then the types up to 50-meter depth, just based on the access information that it has. So I realized that it gives you something. Our wind actually is very low. So sometimes we end up using wind from outside, 25 meters per second and above. I know it is not very far because if I look at Kampala, it was also low for Nile Bridge, but they had to find it, some mathematics to push it to about 35 to 40 because we don't control the future. Temperature variation, they're here, but recently we had up to 35 far north. It was so hot. Then the peak ground acceleration. Now, depending on the axis, Uganda has 3 zones. The western axis is zone 1, the northern, so you can see Africa is on the western axis. So I do agree that it's giving higher value. Then somewhere Camp Central, they're having 0.1, but then towards Soroti 1.6. So the Soroti area, the eastern axis also is zone 2, and the central is actually zone 3. So it's slightly mild. And also for quick fix and someone to have a pre-feasibility study, you have the different type of soil. You can see here clay, silt, and sandy clay with moderate bearing capacity, sandy loam with Wakisa's dark clay soil with high moisture, Mukono ginger, sandy, then volcanic soil with high mbale, lateral soil with good load bearing capacity, Soroti, Gulu, sandy clay with deep rock layer, deep, so you have to go. So clay loam with moderate, that's a Lira. Arua has some stable foundation, that is sandy gravel. Mbarara, clay soil with underlying bedrock. Volcanic soil with rocky subsoil, that's it. Fort Poto, Kasese has also rock. So you find actually Masaka, Oyima, Tororo, Kotido, Nebi, Ntungamo, they have quite a number. This table provides estimated soil condition based on available geological surveys, soil types. Now this, of course, now we shall share with our students. They can do a bit of reading, and then we have about 4 Master of Structural students in Makerere. I think we shall find time and share with them this literature so that they can do some more reading to compare. Oh, good. Thank you so much, ladies and gentlemen. I have done my sharing. It's upon you to look at it and also advise me how to move forward. Thank you, and enjoy ED tomorrow. Thank you. Bye-bye. Where is the ghetto?